Hello everyone and welcome to chapter 13 called Kinetics of a Particle. So let us start with a definition or a review of the concept of kinetics. We know that kinetics deals with the relationship between the change in motion of a body and the forces that cause this change. So what we're primarily interested in this chapter is the forces that cause motion. So we want to identify the different force components that cause a specific motion. And to do so, we'll make extensive use of Newton's second law, which states that sigma F is equal to ma. Now let us look more closely to this equation, sigma F equals ma, and let us conclude a couple of things. First, one can say that F and A are directly related to one another. This means that A is proportional to F. Now let us look at two examples that would help us understand the physical interpretation of the equation. So let us imagine a box and we just apply a force on the horizontal axis to that box. Now what would one expect is that the box would start moving, right? And our intuition tells us at first that this motion would actually be a constant velocity motion. But that's not true, because if you look back at the equation, Newton's second law equation, applying a constant force F would actually cause the box to accelerate at a constant rate AC, which is proportional to F. So this is the main interpretation of the equation, a force that dictates acceleration and not motion. So if you apply a constant force to a box, the box would start accelerating at a constant rate. It would not move at a constant velocity. So motion is not related to the force. Force is related to the acceleration, which causes motion. Now looking at the second term from the right hand side, which we have not discussed yet, which is m. So one can say that m provides resistance to motion. So the bigger m is, the smaller the acceleration would be. And finally, one needs to note that sigma F and A have the same direction. So if you apply a force in the horizontal direction, let's say in the positive sense, the box would also move in the positive sense. Now let us look visually at the equation. We have sigma F is equal to ma. I'll present here two different diagrams which are really important to solve any problems from chapter 13. The first one is called the free body diagram, and it actually represents the particle and the forces that are acting on it. Here we can see, for instance, force F1 and force F2. Now what do we actually mean by the summation of forces? Well, you just need to sum the forces vectorially, right? So if you have F1 and F2, the resultant force, which is the summation of the forces, can be found by simply completing the parallelogram, and so you'll end up with the diagonal line being the resultant force. And so from the equation, we know that the resultant force is equal to ma. So we can simply now draw another diagram, which is called the kinetic diagram, in which ma is drawn as being proportional to the resultant force. So you can see here that ma is slightly smaller than the resultant force Fr. Now another thing to note when drawing these diagrams or when solving the problem is that one needs to define an inertial frame of reference. And one needs to keep in mind that the inertial frame of reference has to be fixed or have a constant velocity such that the acceleration component remains the same regardless of the selected reference. So if you select a reference frame, let's say that's moving at a constant acceleration, when you're calculating the actual acceleration of your particle, this value would actually be flawed. It would have a sort of noise because of the moving reference frame. Now if the reference frame is fixed, or it has a constant velocity, whatever reference frame you pick, the acceleration component you would get for the particle under analysis would exactly be the same. Now that we have talked about a particle and how we could apply Newton's second law onto that particle, let us move forward and discuss systems of particles. So in this figure, we have particle 1 and particle 2, and they are both connected with a probe. And so we'd actually want to analyze the system as a whole. But to do so, let us first work on a single particle as we did before. So if we take particle 1, and we apply the free body diagram and the kinetic diagram, one has the following of a particle. Let us work now with the system of particles. So in the schematic here, we're working with two particles, particle 1 and particle 2, which are both connected with a rope. Now, if we want to sketch the different forces acting on the particles, we have external forces, which are drawn here in red, Fi and Fi, and internal forces, which are due to the connection between the two particles, and that's Fi and Fi. Now, if we want to draw the kinematic diagram and the free body diagram for the first particle, we'll end up with the schematic shown below. So you have small Fi and big Fi acting on the particle, and that's equal to m times ai, which is the acceleration of that particle. So one can then write mathematically for that given particle, let's take particle 1, that Fi plus small fi is equal to mi times ai. So that's the second law, Newton's second law, acting on the particle itself. Now what happens if we consider both particles and the rope as a single entity, as a system? Now if we draw the free body diagram, we actually have both external forces, Fi and Fi, acting on the overall system. Now notice that the small Fi components, or the internal forces, no longer appear when we draw the free body diagram, and that's because they cancel out. So if you notice from the first schematic, the first Fi is directed towards the right, while the second Fi is directed towards the left. And so summing both of them vectorially would actually give us 0. And that's why they do not appear in the free body diagram of the system. Now similarly, if we want to draw the kinetic diagram for the system, we'll simply represent it with a vector named m total ag. So how can you write that mathematically as well for a system? So sigma fi, so the summation of the external forces, remember internal forces do not show, is equal to the summation of the masses mi times the accelerations ai. And now if we take the center of gravity of the system, one can write that the summation of the mai components is equal to mt times ag. And so doing the replacement, we get the final equation for a system, which states that sigma fi, the sum of the external forces, is equal to the total mass times the acceleration of the center of gravity. Now what's important in this section is the fact that making use of a system instead of the particles themselves actually got us rid of one of the unknowns. So in our equation now, Fi does not appear at all, and so we could make use of that in solving problems. Because remember, the less number of unknowns you have, the easier the problem gets.